SwayamPrabha. Digital India. Educated India.
Hello, in this lecture we will continue our discussions on particle kinetics. I will show you through some examples the application of Newton's laws of motion, and the first problem that we have today is this of a heavy chain on a rigid surface, part of which is smooth, which means frictionless, and part of it is rough, which has friction. The problem says a heavy chain with a mass rho per unit length is pulled along a horizontal surface consisting of a smooth section and a rough section by a constant force P. You can see in the figure. If the chain is initially at rest on the smooth surface with x equal to 0, x is shown here, and if the coefficient of kinetic friction between the chain and the rough surface is mu k, determine the velocity v of the chain when x equal to L, which means the chain is being pulled and we have to find out when x equal to L, that means the whole chain has come onto the rough surface, when the whole chain is on the rough surface. So, under this condition we are going to find out the velocity. You have to assume that the chain remains taut and thus moves as a unit throughout the motion. A linked chain can collapse, as you can understand, because it cannot sustain compression. If you try to compress a chain, it will collapse. Here we will assume that it is always in tension, and the second part of the question, what is the minimum value of P that will permit the chain to remain taut? This is the second part of the question which we have to find out. So, we have to find out the value of P for which there is no collapse. The first step is choice of coordinate system and setting up or drawing the free body diagram. The coordinate system is trivial, it is one dimensional motion. I have taken the x coordinate as shown. In the free body diagram, you have to understand a few things. The net weight of the chain is shown here. So, this is the net weight of the chain, and the net normal reaction from the ground is shown here with n. But this friction force mu k times rho x g, why this rho x g? Because it is only part of this chain that is facing the friction. How much? The x part, the weight of or the mass of this part of the chain is rho into x, into g is the weight of that part of the chain, and multiplied by the coefficient of friction, because it is slipping, it is sliding on that surface. So, the force of friction is mu k times the net normal reaction on the rough part, which is rho g x or rho x g, and P is the horizontal force which pulls the chain. Equation of motion is straightforward in this case. Total mass of the chain times acceleration of the chain is the net force acting on the chain. Now, the mass times acceleration, there is only acceleration in the x direction. I call that as v dot, acceleration as v dot, and mass of the total chain is rho times the length of the chain. Mass times acceleration is net force. Net force in the horizontal direction is P, and that you can see from the free body diagram. In the horizontal positive x direction is p, and the friction opposes the motion, therefore, it is minus mu k rho x g. So, that is the net. So, p minus mu k rho x g is the net force acting on the chain in the horizontal direction. Now, here you see that v dot, which is acceleration, is a function of x. Because it is a function of x, therefore, I transform it to the acceleration to v dv dx. This we have seen many times before, because our acceleration is a function of x. If I integrate with respect to x, then on my left hand side I get v x square. So, v square by 2 into rho l of course remains. So, v square by 2 times rho l is equal to p is a constant, p times x, and here mu k rho x g, that becomes half of x square, half of mu k rho g x square. So, that is the integration over x, and there is an initial condition. At x equal to 0, the chain started from rest, and you can check that the constant of integration in this particular case is 0, because the chain starts from rest at x equal to 0. You can see that when x is equal to 0, velocity must be 0. Therefore, my velocity expression is this under root expression, straightforward algebra, and finally, the velocity at x equal to L, that is what we have to find out. This is the velocity for arbitrary x starting from x equal to 0 up to x equal to L, that is where we want to find out the velocity. Therefore, if I just substitute x equal to L in the expression of Vx, that gives me the velocity when the whole chain has transferred to the rough side. The second part of the question was finding out the force P required so that there is no collapse, tension does not go to 0, that means the chain is always taut. Now, when will the chain be always taut? When there is a positive tension. Now, in order to have a positive tension, you must have positive acceleration. Why? Because this part of the chain has no friction force. Therefore, if acceleration goes to 0, it is going to move. If acceleration becomes negative, which means the whole chain, if it starts decelerating, this part of the chain will never be able to feel that deceleration, because the chain cannot transmit compressive force, it will collapse, therefore, it will start collapsing. Therefore, the condition that this chain should not collapse is that its acceleration should always be a positive number, right, it should always have a positive value. If it becomes negative, that means it starts decelerating, then the part of the chain which is on the smooth side will keep moving, it does not know how to stop, because there is no resistive force on that part. So, it will keep moving at constant velocity, whereas the other part of the chain decelerates. Therefore, to prevent collapse, my acceleration must be greater than or equal to 0. If it is equal to 0, then the tension goes to 0, but if you want to have the tension maintained, then it must be greater than 0. For that, you can see from here that acceleration will be positive if p is greater than this value. This is very important in trains. In trains, braking is done on all the wheels. The reason is, if only the engine brakes, if only the brakes are applied only at the engine, at the locomotive, then the rest of the chain, rest of the train will try to collapse onto the locomotive. right. So, if you do not brake on all the wheels, then there will be a collapse of the train. The train will I mean there will be tremendous compressive stresses developed between the coaches at the links, and that may lead to accidents. So, in a long train you have to have any train, you have to have braking on all the wheels. The next problem is about connected bodies, which we have discussed in the previous lecture. This says 3 masses are suspended as shown. The pulley P2, which you can see here, is initially locked to prevent any motion. If P2 is locked, then this 3 kg and 2 kg mass, because they are in imbalance, if you do not lock P2, then it will start rotating. 3 kg mass will apply a greater force, so it will have a tendency to go down. But suppose P2 is locked and the string is not slipping on P2, then I can lock this configuration in static equilibrium. You can check that it will be in static equilibrium if P2 is locked, because here you have total mass as 5 kg, so total weight will be 5 times g. Here you have 5 kg, total weight will be 5 times g. Therefore, this will be in static equilibrium. Now, the question is, if I suddenly open that lock, if it is suddenly released, determine the tension in the strings and the acceleration of the masses. Neglect the inertia of the pulleys and friction at the bearings. Therefore, the pulleys are massless and bearings are frictionless. First, we start with the coordinate system. As usual, the first step in applying Newtonian dynamics is set up the coordinate system. I have chosen the coordinate system as this y coordinate vertically downwards as positive. Therefore, all my velocities of all these bodies, the masses and the pulley P2, which will also move, they are all taken downward, because they are unknown. So, I can take it in any direction. Unknowns can be taken in any direction. I am taking these velocities as downwards. Then the second step is drawing free body diagrams. This is the free body diagram of the 5 kg mass. You have 5 g, this is the weight, and tension T1 upwards. The pulley P2, you have the tension T1, which goes from the 5 kg weight, same tension applies here. So, tension here, which I call T1, is same as the tension here, which is T1, because the pulleys are inertialess and there is no bearing friction. The other two masses 3 kg and 2 kg, you can draw the free body diagram similarly. And remember, in drawing free body diagrams, we are always using Newton's third law. Now, our free body diagram is ready. We move to the next step, which is writing down the kinematics, and we have discussed the kinematics of such systems, string connected, inextensible string connected systems. In this case, if you apply that kinematic relation for pulleys that we had discussed for P1 in pulley P1, this is for pulley P1. So, this is for pulley P1. Velocity, you see velocity of this point and this point is what we look at. This point velocity is same as V5 and this point velocity is Vp2. Therefore, V5 velocity of body 5 plus velocity of P2 must be equal to 2 times velocity of P1. Now, velocity of P1 is 0 because it is fixed. This relation we had derived earlier. So, this is one relation. The second relation comes from this pulley P2. The second relation comes from this pulley P2. And if you look at 2 points on these 2 parts of the string that is going over pulley P2, and also observe that V3 and P2 are in the same direction away from the pulley, similarly V5 and Vp2. Okay. So, for pulley P2, V3 velocity of body 3 plus velocity of body 2 must be equal to 2 times velocity of the pulley. From here, if I eliminate Vp2 from these two relations, if I eliminate Vp2 velocity of pulley 2, then I obtain this relation of velocities, and by differentiating with respect to time I get the acceleration relation. Now, this is this relation, thus this relation relates the acceleration of the 3 masses. Therefore, our first equation is the acceleration relation, which comes from our kinematics. Then we move on to applying Newton's second law, the equation of motion. Mass times acceleration is equal to the force, net force on individual particles that we have now separated. We will apply Newton's second law to the individual mass points and see how we can solve the problem. For the 5 kg mass point, 5 times 5 is the mass times acceleration is a5 is equal to the net force on the 5 kg mass. Remember, force has to be represented in the same reference frame as we are doing the kinematics. Therefore, this 5g, the weight is acting vertically downwards, therefore, that is positive on the right hand side as a force, and tension is acting vertically upwards, that is negative. So, 5g minus T1 is the net force on the 5 kg block. Similarly, the 3 kg block, 3 times acceleration of the third block is equal to 3 times g minus T2. Similarly, for the 2 kg block, and finally, for that pulley P2, which is massless, therefore, our left hand side is 0 and the right hand side is the net force acting on that pulley. T1 is acting upwards, so minus T1 and plus 2 times T2, as you can see from here. What are the unknowns in this system? A2, A3, A5, T1, T2. So, there are 5 unknowns, and you can note here that there are 5 equations. One comes from that kinematics, the other comes from the equations of motion. We have 5 unknowns and we have 5 equations we should be able to solve. The way I solve it is I determine A2 from here, A3 from here, A5 from here, and substitute in the kinematics relation 1. Let us see what happens. A2 is g minus T2 by 2, g minus T2 by 2, that is A2, and minus A3, A3 is g minus T2 by 3. So, that is A3 minus A3 minus 2 times A5, this is A5. From here, by plain algebra you can get this relation. It is a relation between T1 and T2 and of course, g, which is known. We have another relation between T1 and T2, which is given by 5. Therefore, I can solve. Using 5, I get values of T2 and T1, this straightforward algebra. And once I have all these things, so this is T2 and T1. Once I have T2 and T1, I can substitute in 2, 3 and 4 to solve for the acceleration of the mass points. So, that completes the solution of this problem. So, the details I leave to you to complete. We will go to the next problem. If the coefficients of static and kinetic friction between the 20 kg block A and the 100 kg block or cart B are both essentially the same value of 0.5, determine the acceleration of each part for A. P is equal to 60 Newton and P is equals to 40 Newton. You can see the figure, two blocks are placed one over the other. The lower block is on wheels, which means that it is going to be frictionless. The connotation is that it is frictionless. This problem is taken from the book of Merriam and Craig. There is friction at this interface. At this interface, you have friction and mu s, static coefficient of friction and kinetic coefficient of kinetic friction, both are equal as given in the problem statement. And there is a force that is being applied through this inextensible string, which goes over a pulley which is attached to only the 20 kg block. The response of the system is asked for two values of P, one is 60 Newton, the other is 40 Newton. Now, this is an interesting problem because this will demonstrate how the force of friction is dependent on the whole dynamics of the system. Let us see. First step is to fix up the coordinate system. As I have shown, the coordinate system is x y, x is to the right, y is vertically up, and drawing the free body diagram, which I have drawn here. The pulley is frictionless, therefore, the tension in the two parts of the string is same P. I have shown the weight of the 20 kg block, normal reaction. The friction force, you will notice I have kept it as F. I do not know a priori whether it will stick or it will slide. I am not sure whether it will stick or slip. Therefore, I do not know really the friction force to begin with, and this is very important. Before the friction force can be decided by the dynamics, and this is what this problem shows us, and this is what I am going to demonstrate. Okay. Then on the 100 kg block, using Newton's third law, the normal reaction is N1 in the vertically downwards direction, force of friction is opposite to the force of friction on the 20 kg block, weight of the 100 kg block and net normal reaction from the ground on the 100 kg block. So, that is, that completes the free body diagram of the individual blocks. The first case, force is equal to 60 Newton. Now, we have to enumerate what are the possible motions. The first possibility is that they will stick and move together. Therefore, x a, the motion of block A, is same as motion of block B. X a is equal to x b, there is sticking. The second possibility is x a not equal to x b, which means there is relative motion, there is sliding, that means there is slipping. Let us start with case A, the motion possibility A, which means the displacement of both the blocks are same, displacement same, which means velocity will be same, acceleration will be same. Let me make a simplifying redefinition that x a is equal to x b is equals to x, because they are same. Now, I write down the equations of motion of the individual blocks. This is because it is now moving as a whole system, the total mass is 120 kilogram. So, total mass times acceleration of the whole composite mass block is equal to 2 times P, that is the only horizontal force, and that is equal to 120 Newton, because P is assumed to be or taken to be given to be 60 Newton. Now, that is the equation of motion in the horizontal direction. and from here I obtain the acceleration of the composite thing 120 kg block. So, it is 1 meter per second square. Now, we check for sticking or slipping condition, because we have assumed sticking. Therefore, our force of friction at the interface divided by the normal reaction at the interface must be less than equal to the given value mu s, which is 0.5, and mu s is equal to mu k. Therefore, F by N1, the force of friction divided by the normal reaction at the interface, must be less than equal to 0.5. We have to find out the force of friction and the normal reaction. So, for that I look at body A only. Now, I am looking at body A only. For body A, I write down the equation of motion, which is 20 is a 20 kg block. So, 20 times acceleration is equal to 2p, the total horizontal force, minus F, that you can check from this free body diagram. This is indeed the equation of motion for the 20 kg block in the horizontal direction. In the vertical direction, there is no acceleration, therefore, 0 must be equal to summation of all forces in the vertical direction. Vertical direction, weight, so minus 20 g, because I have taken upward direction as positive, remember. So, minus 20 g plus N1 follows from the same free body diagram. From here I can solve for F and N1, because x double dot is known, and if you do that, you will get force as 100 Newton, that friction force as 100 Newton, and normal reaction is 196 Newton, and if you take the ratio, it comes out to be 0.51. This ratio is 0.51, it is greater than mu k, which means to sustain this friction force you need a friction coefficient of 0.51, which is greater than the given coefficient of friction, static coefficient of friction. Therefore, this cannot sustain sticking, this contact cannot sustain sticking. Therefore, this will definitely slip. Our sticking assumption, or the first case possible motions, one of the first possibility that we had considered, is therefore wrong. We come to the next possibility, which is slipping. Once it is slipping, then I definitely know the force of friction will be mu kinetic coefficient of friction times the normal reaction at the interface. This is known, because it is slipping, it is sliding. Now, I have to write for the individual blocks, because these are now motions of these two blocks are different. Therefore, for the 20 kg block, from the free body diagram of the 20 kg block, I can easily write down this equation of motion, and here I have taken the force of friction as mu k times N1 and directed in the negative x axis direction. In the vertical direction, there is no acceleration, it is only force balance in the vertical direction. So, 0 is equal to N1 minus 20 g, the weight. For the 100 kg block, the mass of the block 100 into acceleration of the block is equal to the force of friction, that is the only force in the horizontal direction on the 100 kg block. So, and that is equal to force of friction is mu k times N1. And in the vertical direction for the 100 kg block, there is no acceleration, therefore, it is balance of forces, N2 acts vertically down upwards, N1 acts vertically downwards, as you can see from the free body diagram, and the weight, which is 100 kg 100 g, is vertically downwards. Now, you can solve, because we have unknowns as x a and the motion x a and x b, and of course, N1 and N2. So, x a, x b, N1, N2, we have 4 unknowns, we should be there are 4 equations we should be able to solve. I have solved x a double dot and x b double dot, which gives me the acceleration of the two blocks. The acceleration of block A is 1.1 meters per second square, and x b double dot is 0.98 meters per second square, both are positive, therefore, both will move to the right. Next, we go to the case with P is equal to 40 Newton. The possible motions, again we can have these two motions, sticking, where both the blocks will move together, or sliding where the motions will be different. Equations of motion follow the same pattern as we have discussed. So, x a equal to x b equal to x, I am making a simplification. I am writing down the equation of motion for the full system. So, 120 times acceleration is the net force, which is 2 p, which is now 80 Newton, and x double dot turns out to be 0.67 meters per second square. Now, we check again for sticking, because we are assuming sticking. Let us see if it really sticks. So, I have to calculate the force, friction force acting at the interface, and divide it by the normal reaction at the interface, and check that it is less than mu s. For body A, again 20 kg block, I look at the equation of motion in the horizontal direction, the equation of motion in the vertical direction, which is basically force balance, and from there I get force of friction as 66.6 Newton, and the normal reactions remains the same as 196 Newton. And if you look at this ratio F by N1, it turns out to be 0.34, which is less than mu k. Therefore, this this coefficient of friction which is 0.5 can sustain this contact. That means, it will stick, and therefore, our acceleration is 0.67 meters per second square, which we have determined. So, just to summarize what we have discussed, we have looked at the kinetics of particles, some problems on kinetics of particles, and all these 4 steps which I keep mentioning, I have demonstrated how to use them to solve these problems. So, here I will close this lecture.